Good afternoon, and welcome to Practical Approach to EMI Diagnostics, presented by Microwaves and RF. This webcast is sponsored by Tektronix. My name is Nancy Friedrich, and I'm Editor-in-Chief of Microwaves and RF. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow Help button below the slides. You may also download the slides by clicking the green folder icon at the bottom of your screen. We welcome your questions during today's event. Just type your question into the question window on the side of your screen, and then hit the Submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. Please also be aware that today's sessions are being recorded and will be available on the Microwaves and RF website within the next week. You'll be notified by email when the archive is available. Let me now introduce today's speaker. Robin Jackman is a Senior Application Engineer for Tektronix. With over 25 years in the industry, he's held a wide variety of positions, including spectrum management, systems design, product development, and regulatory affairs. Robin began his career with the Canadian government after graduating from the Microwave Technology program at Conestoga College in Ontario, Canada. Now I'm happy to turn things over to our presenter. Robin, the floor is yours.
Thanks, Nancy. Hi, everyone. My name is Robin Jackman, and I'm an application engineer with Tektronix. Today, for the next hour, we're going to be talking about EMI troubleshooting. We're going to take a look first at some EMI EMC definitions, look at pre-compliance scanning versus compliance scanning, and finally, we're going to look at debugging issues, looking at specific measurement setups and discussing some best practices. EMI specifications affect us all. The final destination and use of our products defines which EMI specifications we need to follow. Are we going to be using the product in a home, an industrial space, a heavy industrial space? Further, EMI specifications are made by specific industries, for example, automotive or the military. In general, we have two types of EMI measurements. Conducted measurements, where we're looking at the energy we put back onto the AC mains, or radiated measurements, looking at unwanted energy that's coming from the device under test. A third subset that we're not really going to address today is susceptibility or immunity measurements, and that particular category has both conducted and radiated measurements as well. In conducted measurements, the basic setup is an EMI receiver, typically defined by CISPR 16-1-1, some software, and the software could be supplied by the manufacturer of the receiver, or there are third parties available. We also have a LISN, and we have a limiter. Now, the LISN is very important in this particular setup because not only does it connect our device under test to the AC mains, but it also protects our instrument and provides a 50 ohm interface for us to take our measurements from. The limiter is in place for additional protection so that we don't damage the front end of the EMI receiver. The software does two things for us. It actually controls the test itself, but it also generates the test report, and the test report will be specific to the EMI specification that you're working to. Radiated measurements are a little bit different. We have specific distances we must be from the device under test. We must provide some form of RF isolation. It could be an anechoic chamber or an open-air test site. And we need to characterize the emissions coming from the device 360 degrees around it. Now, this could take quite a long time if we had an EMI test that we had to do to 26 gigs, and we had to go right the way around the product. These tests can take so long that oftentimes what a test house will first do is what's called a peak scan. In a peak scan, we look at the max energy coming from the device, and if we find a particular element that's suspect, we will zoom in on the suspect element and apply the EMI filters or the EMI detectors on those spot frequencies. I'll talk more about EMI detectors a little bit further on. When it comes to EMI characterization, we basically have two perspectives. We have compliance and pre-compliance. Compliance measurements involve a large capital outlay, not just for the equipment, but also for the physical setup. To build an anechoic chamber of 3 meters or 10 meters is very, very expensive. Big companies can support these costs, but very often smaller companies can't. So smaller companies will use an external test house to do the compliance measurements for them. The goal for us is to go to the external test house as little as possible. Really, we only want to go there once. If we have to go there more than once, it not only incurs extra cost, but a significant amount of time as well. Pre-compliance measurements, on the other hand, can be done in-house. Testing for EMI issues throughout the design process is a really positive thing. We can catch EMI problems much earlier in the design cycle and fix them before they become a bigger problem later on. No one wants to fix an EMI issue when we've already got the product in its final packaging, for example. But we still have to go to the EMI test house. Even if we do pre-compliance scanning, we ultimately have to get our certification from the test house itself. Now, having said all that, pre-compliance scanning doesn't have to take a long time, and it doesn't have to cost a lot of money as well. So what do we need for pre-compliance scanning? From a pre-compliance perspective, what I want to do is replace the EMI receiver with a signal analyzer or a spectrum analyzer. Now, we do have to be a little bit careful there. We have to understand what the differences are between an EMI receiver and a spectrum analyzer. Do we have the right resolution bandwidths? Do we have a lot of trace points, or do we have a few trace points? Do we support dwell time? Do we support the CISPR detectors? Do we support antenna factors, which are not the same as antenna gain? On the physical setup itself, we'll also need the antennas to perform the experiments. Biconical antennas are very popular. We may be able to use a log periodic. We will need a tripod. And depending on the distance the antenna is from our signal analyzer, we might need a preamp in the situation as well. People are often a little bit confused about this particular situation because if you didn't have an anechoic chamber, are the measurements valid? And the short answer is yes. We may have to use a boardroom. We may be able to do it in our lab if the lab is RF quiet enough. Or I've even seen people make measurements in a parking garage. Ultimately, it's very difficult to duplicate exactly what the EMI test setup is in the test house. We can make a very accurate approximation, but it's not the same. We need to understand the compromises in using a signal analyzer versus an EMI receiver, and we have to pay attention to as much detail as possible. So let's look at a swept-tune spectrum analyzer. Swept-tune spectrum analyzers have been around a long time. We call this a traditional architecture. In a swept-tune analyzer, we know that we have low frequency on the left, high frequency on the right, and power logarithmically on the y-axis. In general, we get good dynamic range and good sensitivity, but we have two measurements we can make. We can make frequency versus amplitude and amplitude versus time. This is important because very often when we're doing an EMI peak scan and we spot a frequency of interest, we'll actually put the spectrum analyzer in what we call zero span mode and look at the power versus time of the signal, trying to figure out what its periodicity is. The key thing there is that the power versus time measurement is seen through the eyes of the resolution bandwidth filter. So we're only going to see as wide as that resolution bandwidth filter can see. When we look at the architecture here, past the envelope detector, we have the video bandwidth filter. In some EMI specifications, we have to pay attention to the video bandwidth filter. It's a post-detection low-pass filter that allows us to smooth the trace. When selecting a spectrum analyzer to do EMI pre-scanning, we have to pay attention to not only the frequency range of the detectors, but also the number of trace points that the instrument can give us. Some low-end spectrum analyzers will only give us maybe 501 or 801 trace points. That wouldn't be enough if we were looking at gigahertz of spectrum. I'd want to be able to increase that number into the thousands so that I get better frequency resolution. Real-time signal analyzers are a little bit different than swept-tuned spectrum analyzers. We still have a preamplifier and a stepped attenuator and some filtering in the front end, but there's many differences when it gets into the intermediate stage. In this particular example, we have an ADC which is going to create time domain samples. We're going to digitally downconvert and create I and Q. And I and Q is actually going to go into a buffer as well as go into a real-time engine. The term real-time comes from the fact that we don't drop any samples after we digitize in the IF. From a speed perspective, it's significantly faster than a swept-tuned spectrum analyzer for narrow resolution bandwidths, and I have a slide that talks about that in a little bit. But because we are looking at the spectrum from an IQ perspective, I get to do what's called multi-domain analysis. I can look at frequency, amplitude, and phase versus time in a very, very correlated manner, meaning if I put a marker in one domain, it automatically tracks in another one. Now from a EMI scanning perspective, that's not helpful, but from an EMI diagnostic perspective, it's very helpful. I noticed in the pre-show polling, a lot of people were using oscilloscopes for making EMI measurements. Oscilloscopes themselves are very interesting instruments. When we look at their architecture, they're actually designed to take signals from basically millivolts to kilovolts. Scopes are designed to handle a large number of different types of probes. We have active probes, we have passive probes, we have single-ended probes, we have differential probes. All of this means that the input to the oscilloscope is quite complex. When I think about sensitivity, oscilloscope sensitivity is in the millivolt range. Spectrum analyzer sensitivity is in the nanovolt range. So we're going to see a lot more detail with a spectrum analyzer versus using an oscilloscope. Depending on the oscilloscope you have, the FFT capabilities, or the ability for us to visualize the spectrum with the scope, varies widely. If you have a general purpose oscilloscope with an embedded operating system, you may or may not get full control over the FFT calculation, meaning you might not be able to set reference level, you might not be able to set resolution bandwidth, and you might not be able to select detector type. All of this is going to affect how well we do the EMI scanning. Models are available over a broad price versus performance range, and you can even get into some Tektronix Windows scopes that have spectrum analyzer applications that can run on top of them. It can directly turn the oscilloscope into a spectrum analyzer. But even when we do that, we can't actually fix the insensitivity on the front end of the oscilloscope. One area where I really like to use oscilloscopes is for low frequency application with the high resolution sampling mode that's in the oscilloscope itself. We can get extremely high dynamic range, extremely high frequency accuracy when we're looking at very, very low frequencies. And I'm talking here about AC mains frequencies. When we're considering spectrum analyzer sweep speed, there's a large difference between a swept-tuned spectrum analyzer and an FFT analyzer. In general, FFT analyzers will be faster than swept-tuned spectrum analyzers when we're looking at resolution bandwidths below 30 kilohertz. If we have resolution bandwidths above 30 kilohertz, then typically swept analyzers are faster. Now, when we consider it from an EMI perspective, we also have another couple of considerations. In an EMI environment, we have to be considered with dwell time, because some of the detectors that we use in the EMI environment require us to stay on frequency for a set amount of time so that our integrated power measurement is taken over time. EMI receivers and spectrum analyzers do not sweep the same way. We are a swept-tuned signal analyzer for your average spec A. We're a stepped-tuned receiver. And the EMI receiver can actually define the number of steps that it will take between the low frequency and the high frequency in a specific range. This is significantly different than a regular spectrum analyzer, where all we can control is the actual sweep speed itself. when it comes to detectors, and when I'm speaking about detectors, specifically it's about power detectors in EMI receivers versus spectrum analyzers. EMI receivers employ typically an EMI peak, an EMI average, and an EMI quasi-peak. Now, these are the three most popular detectors. I'm going to start at the bottom here. The quasi-peak detector has been around for a long time. It's essentially a detector that allows us to measure the annoyance of the signal. For example, we could have a very, very large signal, but that's not on very often, would be weighted significantly lower than a low amplitude signal that was on all the time. In general, when we think about a quasi-peak detector, the dwell time per step could be upwards to 1 second. If we had to use that detector over gigahertz of spectrum, it could take significantly long time for us to scan with that quasi-peak detector, which is why very often people like to use a peak detector. An average detector is different than the average detector that you'll find in your average spectrum analyzer. And I know I use a lot of averages there. In general, what we're talking about here is the ability for the average detector to incorporate or integrate power over time. And 100 milliseconds is a very common time period for us to incorporate this average detector. It's unlike an average detector in a regular spectrum analyzer, which will give us an instantaneous average or an average of the number of samples that are in the detector at a specific time. And that's the difference. EMI time-weighted detectors look at power over a time period. I bring up peak detectors or EMI peak detectors because they are actually the safest detector that we can use. If all we did was use a peak detector during our scans, we can say with some confidence that if we pass a peak detect, we will pass a quasi-peak detect. And this is why, as I said earlier on, EMI houses like to use a peak scan first because peak scanning takes the least amount of time. If they find a suspect frequency while they're peak scanning, they can switch over to quasi-peak scanning and do a spot frequency test on that particular element. They can save a lot of time this way because it would be unfortunate for us to spend hours scanning a specific product only to have the product fail and have to return it to the customer anyway. One other note about the actual detector type is that the shape factor of the resolution bandwidth filter or the power detector in an EMI receiver is different than a spectrum analyzer. In fact, it has a lot steeper slopes. In some spectrum analyzers, you can purchase an add-on package, an EMI package, or if you look at the RBW settings, you might be able to set a CISPR setting. And that will actually change what the integration span of the RBW actually is. Here I have an example of a Tektronix RTSA. This is actually an RSA 5126 doing a basic radiated test. Now I'm going from 30 to 26.5 gigs here, and I've set it up into 4 ranges, and you can see that I'm using logarithmic frequency scaling. In this example, I actually used the max number of trace points possible, and for 4 ranges, that would be a little over 41,000 points. You can see here that I have a table of values that the analyzer has found. I see 2 that are in red and a bunch of other ones that are not in red. In this particular example, the 2 frequencies that are in red would be actual failures. They're above the prescribed limit. Those other peaks that are identified were identified because I set the detection threshold about 10 dB less than the absolute threshold for the test. Meaning if I had any carriers that were within about 10 dB of the actual limit itself, I wanted the system to identify them for me because we're doing a peak scan here. Now, many of these might drop away in a quasi-peak scan, but these are the ones that I would want to be concerned about. As of interest here, it took about 15 seconds for us to do this peak search. That's actually fairly quick. If we were looking at this from a swept-tuned spectrum analyzer, it may or may not be quite as fast. And if we used a narrower RBW, and in this particular setup I was using 9 kilohertz for the first and second ranges, then 120 kilohertz in the third range, and then 1 megahertz in the final range. Same instrument now in this particular slide, but I've switched over. I'm using a quasi-peak detector. Note how long it took to do this particular scan. It was 117 seconds for 30 megahertz to 216 megahertz. That's a fairly long period of time. And we did the integration, and we found that we only actually had 5 carriers identified. And with quasi-peak detection, none of these 5 were above the limit. They were all below the limit. But because I specified my threshold to be within 10 dB of the absolute limit, it still identified them as could be a problem for me. With this information, I could go back into my design and find out specifically where these frequencies are being used, and if necessary, take corrective action. Of note here, though, this is only less than 200 megahertz, and that took 117 seconds. If I have to go gigahertz through gigahertz of spectrum with a quasi-peak detector, it will take a long time. So what if we have a spectrum analyzer that doesn't have all of those fancy scanning algorithms for us? What can we do? The technique I like to teach people is called subranging. Basically, if we have a simple spectrum analyzer, what we can do is set up one specific range for each band of the test of interest. So in this test here, I'm looking at 30 megahertz to 88 megahertz, which is the first range from the previous 2 scans. In this simple example, I set a 9 kilohertz resolution bandwidth, which would be the same as called out in the CISPR spec. I did a peak detect, and in this case, I have 1,001 trace points. Now, it only took 1 second for me to capture this information. That's not too bad. I could offload this information to a spreadsheet and plot the spectrum data versus the limit line for me to get a better idea of how I'm performing across the complete range. A couple of notes here. As we're doing this scanning, if we don't have some form of anechoic chamber and we're using an open air, or we're in our lab, or we're in our boardroom, we are going to have to figure out if the product we're seeing on the display is coming from the product itself, or is it coming from the ambient RF environment. So there's a couple of things you can do there. Basically, we could turn the product off, do a scan, and then turn the product back on and do a second scan to determine which products are coming from the device under test and which products are there sort of naturally. When we have automated software, you can saw on the previous 2 slides, we could store the information in those tables and then do a table comparison afterwards to subtract out those frequencies we knew were from an off-air source. The rule of thumb here, though, is be careful. Fully characterize your ambient environment so that you can do an accurate job of assessing which products are coming from the device under test and which products are coming from the ether. When it comes to debugging EMI issues, I have some favorite topics, or favorite targets, if you will. The first place I like to go is usually power supplies, and specifically switch mode power supplies or circuits that involve some sort of switch mode. Switch mode operation often leads to ringing, and depending on the amplitude of the ring, it's a ripe place for us to have a source of our RF energy. From an EMI perspective, when we're talking about a specific design, we usually break it down into sources and antennas. Where is the source of the energy, and how does that energy actually leave the board? Second to switch mode power supplies and switching circuits, I often look at clock and data. Depending on the design, you may or may not be employing some form of spread spectrum clocking. It's important for us to know how well our spread spectrum clocking is working. After that is looking at a broad term I call resonances. Resonances could be actual in the board itself. It could be into wiring geometries. It could be into cabling, shielding, and mechanical issues. In general, when I first look at a problem product, I will go to the power supply. Second place I'll go to is what I call the goes-ins and goes-outs. Which signals are going into the device and which signals are coming out of the device? Do we have USB? Do we have Ethernet? Do we have RS-232? What does the cabling actually look like? All of these places are prime candidates for causing us EMI issues. When I'm doing EMI diagnostics, one of my favorite tools are near-field probes. Near-field probes allow us to isolate the source of energy on a specific PCB. And we have 2 flavors of near-field probes. We have E-field probes. Those are the stub probes that you see in the picture here. And we have H-field probes. Those are the loops. In general, the larger the diameter of the loop, the lower the frequency, and the less narrow the focus is on the probe itself. When we're thinking about using an E-field probe, we have to keep in mind that our max sensitivity of the probe is when the probe is fully perpendicular to the PCB. In general, E-fields are associated with sources that have a high voltage but low current. Conversely, when we're thinking about from an H-field perspective, the maximum sensitivity for an H-field measurement is when the probe is perpendicular to the board, or pardon me, parallel to the board, not perpendicular. From an H-field perspective, usually those sources are low voltage but high current. Now, a lot of people say, I want to make a calibrated measurement with my E-field or H-field probe. In general, those probes aren't really calibrated. From a diagnostic perspective, though, that's not much of a problem. From a diagnostic perspective, what we're really looking at is how much change or relative change do we make to our signal. So if we have a spot frequency that we know is a problem and we've tried to mitigate that some way with some shielding or a change in the design, we can measure before and afterwards to find out how much we've affected the change. Now, you don't actually have to buy these probes. The probes are fairly easy for us to make, and there are many instructions that we can get off the internet. What I will say, though, is please be careful. When you're putting together your own probe, remember that if it has a conductive surface and you're sniffing very close to the device under test or the PCB, you don't want to cause yourself any issues by shorting out the PCB during your test. Advanced EMI debug. Tektronix has an MDO4000 Mixed Domain Oscilloscope. This is a really interesting instrument because it combines a spectrum analyzer, a scope, and a basic logic analyzer in one instrument. It has 21 separate inputs that are all time correlated. The spectrum analyzer itself will go anywhere from 50 kilohertz to 3 or 6 gigahertz, depending on the model. It employs a digital down converter and has extremely wide instantaneous bandwidth. In a classic spectrum analyzer, when we're looking at the frequency versus amplitude display, we know that a swept-tuned spectrum analyzer sweeps from left to right and looks at the spectrum through the eyes of the resolution bandwidth filter. A mixed domain oscilloscope doesn't do that. For up to a 1 gigahertz span, it instantaneously digitizes the whole span. So what we see on the left-hand side of the display and what we see on the right-hand side of the display are collected at exactly the same time. Because we're actually performing an IQ analysis here, we also have access to frequency, phase, and amplitude. And it's a little bit different than a regular VSA. So here we have a picture of the front end of the MDO4000. And let's just tear it open here. In Tektronix lingo, we call the 4 inputs, channels 1 through 4, the analog inputs. Here we have a digitizer and record length per channel. And this is pretty much standard when we think of an oscilloscope. Now, on the MDO4000, we also have a digitizer. Now, we also have a block converter, depending on the model you purchase, be it a 3 gig or a 6 gig model. If it's a 6 gigahertz model, there's a block converter. If there's a 3 gigahertz model, there's no block converter. It goes into its own digitizer and then into memory. The key thing between an MDO and other mixed signal oscilloscopes is that we have a global trigger and acquisition control between the spectrum analyzer and the oscilloscope and the basic logic analyzer, meaning I have independent record length for each of the 3 parts of the instrument, but I have common acquisition control. I have a global trigger. If I trigger on the digital side, I cross-trigger the RF side. If I trigger on the RF side, I cross-trigger the analog and digital side. And this lets us do some really, really interesting things when it comes to EMI diagnostics. First, we have to show you how it works. Here we have a classic oscilloscope display. This is actually the display for the MDO4000. People are very familiar with the time domain view we see on the top portion of the display. And people are very familiar with the frequency domain view we see on the bottom portion of the display. The key thing is, how do we link the two together? If you look at the top portion, we call that analog time. That's the if you will, the record length that you collected during a single shot acquisition. Old time would be on the far left. New time would be on the far right. What we have to do is introduce the concept of spectrum time. Because it is an FFT box, we have to have a start time and an end time for the FFT calculation. And that's exactly what spectrum time is. When you're looking at this display here, you can see the small orange rectangle. That tells us when the spectrum that we're looking at happened. So in this particular example, we can see that channel 1, the yellow channel, is on a VCO-enabled line. We can see the label there. Channel 2 is on a PLL control voltage channel. That's in cyan. The purple is the actual digital bus. In this case, we're doing a SPI decode. The spectrum analyzer is tuned to a center frequency of 2.3 gigahertz with a span of 300 megs and a resolution bandwidth of 300 kilohertz. What we can do with the MDO is use our jog shuttle control to actually step spectrum time through analog time. And let me show you how that actually works. In this example here, you can see it's the same experiment from the previous slide. And it's actually a simple radio. A SPI bus turns on a transmitter, and as the PLL control voltage changes from low to high, the output frequency of the transmitter is also going to change from low to high. I'm just going to play the animation now, and we'll see how it works. As we step spectrum time through analog time, we can see how the frequency was changing from low to high. Down below, we see that we have an automatic marker that's tracking the peak signal in the display. In this way, we can fully time correlate the spectrum analyzer to the scope. Now, remember, it's not just an FFT on a scope channel, but it's an independent spectrum analyzer that has record length that's time correlated to the record length of the analog and digital channels. So what does that mean for us? Well, the MDO 4000 has a huge amount of instantaneous bandwidth. In this particular example right here, I'm looking at the output of a switch mode power supply, specifically the DC to DC converter component. When you look at the architecture of the MDO 4000, you see that it can support up to 40 volts DC on the input to the RF connector. In this experiment here, I have a P6150 out probe directly probing a 20-volt DC rail, and we're looking at all of the noise components on that 20-volt DC rail. The top portion of the display is called a spectrogram, and a spectrogram is looking at power spectral density over time. So we have low frequency on the left, high frequency on the right, but time now is on the y-axis. Color in the spectrogram is power. Red is very hot, it's very high. Black is very cold, it's very low. What's interesting about the spectrogram is that it allows us to see changes over time. And that's the missing component from many spectrum analyzers. We don't often get to see how things change over time. The second thing the spectrogram gives us the ability to do is look into the noise floor a little bit more clearly than a regular spectrum analyzer display. I can look for non-randomness in the noise floor to see how a signal is changing over time. For example, it's easy for me to see all of the vertical parallel lines from the harmonics of the switch circuit in the DC to DC converter. But what I can also see is banding horizontally in the spectrogram display. That tells me that there's broad-banded energy there that is varying over time. It's not consistent, because if it was consistent, I would see a consistent color shift. But I can see these horizontal bands, and that means it's changing. In this example here, we're looking at a Class D amplifier. In this specific setup, I have the spectrum analyzer looking at a center frequency of about 250 megahertz with a span of 500 megahertz. So we can see I have got two band cursors set up between 12 megahertz and 108 megahertz. On the top portion of the display, I actually have the analog channels turned off, and I have the amplitude versus time trace turned on. Now, this is not zero span like we have in a regular swept tune spectrum analyzer, because that would only be able to look at the power over time through the eyes of a resolution bandwidth filter. The amplitude versus time trace on an MDO 4000 is actually looking at span power. So we're looking at span power over time now. And we can see specifically that we have these very consistent spikes in the amplitude versus time. I get to control where my spectrum is looking by changing where that rectangular box is. When I move the rectangular box to one of those peaks, I can see directly that there's a lot of spectrum content between 80 and 108 megahertz. When I move spectrum time off of the peak, I see that that content goes away. So it's fairly easy for me to see that when that amplitude is spiking, I'm getting a spike in the spectrum between basically 12 and 108 megahertz. From an EMI perspective, this is not good because that's directly correlating now with the AM or the FM broadcast band. I should point out, though, in this particular experiment, I was using an H-field probe directly over top of the actual switching IC itself. I haven't yet probed it, but in this next slide, I start probing the switch or the control frequency on the switcher itself. Note that when I do a single shot acquisition looking at channel 1 with the amplitude versus time, that my amplitude peaks directly correlate to the rise and fall of that control voltage. That's a huge tip-off for me now. You look at the second slide on the bottom right, you can see that when I place spectrum time directly on the transition, the rising edge of that switch control, I see my spectrum. When I move off of the rising or falling edge, my spectrum goes away. This particular problem had been vexing a customer for a few weeks as they were trying to determine when they were getting this energy. Their regular spectrum analyzer told them they were getting a peak on or about the 80 to 110 megahertz range, but it wasn't telling them how often it was getting it. It was very difficult for them to correlate it to the switch control frequency. With an MDO, this took exactly 12 minutes. In this example here, it's a similar sort of setup. Specifically what I'm looking at is actually channel 1 is on a USB HS or a high-speed line. I'm looking at the amplitude versus time, and I'm looking at the spectrum. In this example, we're at about 339 megahertz or 390 megahertz. We were able to directly correlate the USB message to the spectrum event and see the broad range in the noise floor. And this is where having a gigahertz of instantaneous bandwidth really helps out, because as we're looking at the changes in the noise floor, to our eye, it doesn't actually look that big. When we look at it from an amplitude versus time perspective, it's very easy to see where we're getting peaking in that energy. Further investigation into this problem found it wasn't actually the USB line that was the issue. It was the microprocessor that was generating the USB message is where this energy was coming from. A very difficult problem to solve if we didn't have an MDO and for us to actually decode both an analog, an amplitude versus time, as well as look at the spectrum over time to try and determine what that coincidence actually was. An MDO 4000 supports regular antennas, biconical, log periodic, whatever we might be able to use. It, of course, supports near-field probes. The really interesting thing on the spectrum analyzer input is that it supports our TEC VPI interface, meaning if we have any of our 50 ohm TEC VPI probes, we can directly connect them to the spectrum analyzer input. So, for example, we could use a current probe on the spectrum analyzer input. On the oscilloscope itself, we have models that go right from 100 megahertz to 1 gigahertz, supporting all of the associated probes with those. If we're thinking about it from a power supply perspective, that means now that I could look at current, voltage, and RF simultaneously. And I would be able to de-skew those inputs so I can get a very, very high resolution view of what's going on or what the relationships were between current, voltage, and RF. One of the curious aspects of the digital side is that in our implementation, we can have individual thresholds per pin on our digital input, meaning if you needed to create your own bus of a wide variety of signals, you don't have to have a single threshold to determine high or low for one pod. You can do that on a pin-by-pin basis. at the same time, we can decode up to 4 buses simultaneously. So if you needed to look at RS-232 and SPI and RF at the same time, we could do that. Getting into advanced EMI diagnostics, it's important to look at the persistence displays of real-time spectrum analyzers. A lot of people are making so-called real-time spectrum analyzers now, and in general, up until their maximum real-time bandwidth, they're very, very fast. And that's true with Tektronix spectrum analyzers. What's different with the Tektronix RTSA is that we can step our real-time engine across the complete tuning range of the spectrum analyzer, meaning, as in this example right here, I have to look at an 8 gigahertz span of DPX data, or real-time data. From an EMI diagnostics perspective, where this really makes a difference is in transient or bursted signals. If I know I have a fundamental that is bursted and I'm trying to figure out what the second harmonic content was, in the past I would have to rely on gated sweeping to make sure that my spectrum analyzer was sweeping at the same time my source was actually on. In a TEC RTSA, I can not only define the step size and the start frequency and the stop frequency, I can specify a dwell time as well. So if I wished, I could dwell for 100 milliseconds, 200 milliseconds, and then stitch this data together like you see right here. The probability of intercept is extremely high on a step-by-step basis, which means that my probability of intercept over that complete span is much greater than a regular swept tune spectrum analyzer. Another curious aspect of Tektronix RTSA architecture is that we have parallel spectrum engines. If I have my real-time engine turned on, as you see on the left-hand portion of this display here, I can actually turn on my FFT side, or the buffered side of the real-time engine, simultaneously. So we're looking at the same piece of spectrum, in this case 110 megahertz wide. On the left-hand side of the display, we're looking at the spectrum at about 293,000 transforms per second. On the right-hand side of the display, we're looking at it with a really, really narrow resolution bandwidth, in this case 1 kilohertz. In this fashion, I can look at a signal both fast and wide, looking for transients, and very, very deep as well. In the Tektronix RTSA architecture, I can now trigger on a signal in the left-hand side and have the right-hand side give me a high-resolution snapshot of what happened at that trigger point. And that's one of the fundamental differences between TEC RTSA architectures and many others. When thinking about a TEC RTSA, we have something what we call is multi-domain correlation. So I have the ability to employ a frequency mask trigger or a DPX density trigger, capture a specific moment in time, and cross-trigger other instrumentation. Now that could be a protocol analyzer, it could be an oscilloscope, it could be a logic analyzer. The key thing is that the time correlation is available. So when we need to take information from dissimilar instruments, we can actually put it together in a time-correlated fashion. There are some people who require board-level scanning. Tektronix has a partner, Aprel, in Ottawa, Ontario, who makes the EMI EyeSight system. The EMI EyeSight system is an automated system that employs a robotic arm instead of a gantry. This allows us to support big projects as well as small projects. They have a single 20 gigahertz coverage probe. One of the most interesting aspects of their software is that they're able to do far-field estimation using near-field measurements. For further information, I'd highly recommend you go to their website and you can download the papers that talks about it. EMI Diagnostics affect us all. Pre-compliance scanning will not only save us time, but a lot of resources as well. But we have to pay attention to the tools that we select and recognize their limitations. When we start looking at EMI Diagnostics specifically, near-field scanning will help us pinpoint trouble spots. Analyzing the data from a time-correlated perspective, meaning looking at analog, digital, and RF simultaneously, will speed up our troubleshooting and reduce our debug time. Coincidence is the key. If there's one takeaway from the whole talk on on EMI measurements is that coincidence will help us find the source of EMI problems much, much quicker. Tektronix has been working with Kimmel Gerke Associates for over 10 years, bringing EMI training to the field. The Kimmel Gerke provides these seminars right across North America, usually hotel-based. To find out where they are and when they'll be in your area, you can go to the emiguru.com to find out more information. Your time is important, and we really appreciate you visiting our webinar. Back to you, Nancy.
Thanks, Robin. Well, a few of you have already submitted questions, so we're going to jump right in. While our presenters are answering your questions, please take a moment to answer the feedback form that will appear on your screen. If you have pop-up blocker technology, we ask that you disable it so that you can receive that form. Question 1. Okay, Robin. Someone is saying, I need to do EMI diagnostics on an engine. Do you have any advice related to EMI from an engine, or do you only know about PCB EMI?
Well, that's a very good question. The EMI standards for engines are, of course, a little bit different than EMI standards for other products. We don't really have a conductive measurements per se on an engine because the engine is not connected to the AC mains. Curiously enough, low-frequency EMI is usually of importance to most engine manufacturers because there's a lot of low-frequency clocks that are in the engine control units themselves. Setting up an engine so that you can operate it and run it in some sort of RF shielded area is the bigger challenge, because very often we have a lot of interconnecting cables, fuel, coolant, and the like that has to be accounted for. A lot of the same techniques we use for diagnosing PCB EMI are the same for an engine. For example, if we're going to take our near-field probe, we want to probe around the engine control unit itself, trying to figure out what the EMI signatures are from those modules. It's very, very similar to that of probing a PCB at the same.
Okay.
Got to watch out a little bit on the specifications because most engine manufacturers have to follow whatever the vehicle manufacturer is specifying. So whether it's for a large car company or an outboard motor or a small engine, it'll have its own specific EMI standard.
Okay, that's great. Thanks, Robin. Our next question is on the MDO 4000. Can we control the length of spectrum time?
On the MDO 4000, spectrum time is controlled by manipulating the span and the resolution bandwidth controls. There is no direct control on screen to set the length, but by changing either the span or the resolution bandwidth, that will control the length. So for example, if you see a long spectrum time that you wish to be shorter, you could either narrow the span or increase the resolution bandwidth, and that would shorten the length of spectrum time.
Okay, great. Thanks. Our next question is, why does an average detector scan take more time than a peak scan? Simply put,
in the CISPR specifications, when we're looking at a CISPR average or a CISPR quasi-peak, time is factored into the detection. It's a little bit different than a spectrum analyzer where we would have an average detector at an instantaneous point in time, and it's not the same as a trace detect, which would take multiple traces and average them all together. In a CISPR average, we have a time-weighted detector, which is typically around 100 milliseconds. So for each measurement that we have to take, we would take a minimum of 100 milliseconds, which is why, of course, the scans get so long. Quasi-peak scans can get even much, much longer because it's a minimum dwell time of about 1 second per measurement. So they're significantly longer.
Excellent. Thank you. The next question is, you mentioned in the beginning of your presentation that antenna factor was not the same as antenna gain. Can you please elaborate?
Antenna factor is a function of change of energy versus impedance. And there are some very good documents out there that show the relationship, the mathematical relationship between antenna factor and gain, and how you can use, or taking the antenna factor information, make up a table so that we can fill out the amplitude or gain offset in a specific measurement receiver or spectrum analyzer. Most modern spectrum analyzers have the ability for us to supply a correction or some sort of offset measurement. And usually they come in two forms. There's a fixed amount of offset, and that could be gain or attenuation. And then there's normally some sort of frequency-dependent offset that's also applied. On the Tektronix RSA 5000 and 6000 families, I think we support up to 3 offset tables. So theoretically, you could have the antenna offset or antenna gain, and then as well as a cable or a fixture table as well. And we'll factor all those together when we make the actual measurement itself.
Great. Thanks, Robin. Does Tektronix have any software for protocol compliance? For example, RFID Generation 2 protocol. So it will check if your signal is within spec or not?
Well, that goes a little bit beyond what we were talking about here as far as EMI goes. But the short answer is no. Tektronix does not carry that kind of software. However, the measurements themselves are really not that complicated for RFID Gen 2. And with one of our scopes or our MDO, it's fairly straightforward to make those measurements.
Okay, excellent. We have more questions about the MDO 4000, such as, can I store the IQ from the MDO 4000?
Yes, you can store the IQ data pairs from the MDO 4000 in either a MATLAB format or actually a packed binary file called a TIQ format that is a Tektronix format, but it's open. We publish the spec and how it's made.
Okay, great. Robin, can you tell us why an average detector scan takes more time than a peak scan?
Actually, I think we already answered that question.
Oh, I'm sorry, did we? Okay, sorry. Let's see. Is there a significant difference in the performance of a high-end EMI receiver and a high-end spectrum analyzer?
Yes, there's quite a bit of difference in the performance of a high-end EMI receiver and a high-end spectrum analyzer, and it has to do with the use of a preselector. If you think of a spectrum analyzer, it's a very, very wideband device. So it's possible in the case of a spectrum analyzer that if we had a high-powered signal that was within the passband of the spectrum analyzer, it could affect or overload my spectrum analyzer, causing me to make an erroneous measurement. EMI receivers are designed a little bit differently. They actually have a tracking preselector in the front end of the tuner, which isolates the receiver, the area that we're receiving, if you will. So it gives us an additional level of protection for high-powered signals that are not within the current span, if you will, of the instrument. And that's the major difference when you start looking at EMI receivers versus spectrum analyzers. Typically, your high-end EMI receiver will have much higher dynamic range than a swept-tuned or real-time spectrum analyzer as well.
Okay, thanks. Can you explain a little bit about how to figure out whether a particular noise source is electric field or magnetic field based? For instance, in a 600-volt motor driver with 100 amps of current, what should you look for?
Oh, that's a tough one. It's very difficult for me to comment on each case without actually having a closer look on the actual measurement setup itself. That's a lot of voltage and a lot of current. So the associated fields you're going to get from a setup like that is absolutely huge. Some of the basic techniques we use are to essentially add some attenuation to my measurement. What I really need to do is be a little less sensitive as I probe around the situation. A couple of things when we start considering near field versus far field. If I see something in the near field, I may not see it in the far field. And that's an important point, because if I see something in the far field, I will see it in the near field. It's one of the biggest challenges when we start looking at EMI issues is how much shielding do I need in order to improve a product? I don't want to put too much in, and I don't want to put too little in, but just the right amount. Finding that compromise is difficult. In the case of this motor, I've had a couple of situations where I've had to work on very, very high power situations like this. I like to see both far field and near field data. It's more difficult to not get overload in my measurement device in this particular setup. So having maximum dynamic range possible is usually the first key ingredient. If you try to use an instrument that had poor or very low dynamic range, you probably won't get very satisfactory results.
Okay, excellent. Here's a question about recording. How much spectrum time can be recorded with a real-time signal analyzer?
That really depends on the real-time signal analyzer. The amount of IQ information we can store with a Tektronix signal analyzer is based on two things. Number one, of course, the memory pool itself, and number two, the span. As we change the span, we decimate our data. So if we put some numbers around it, let's just say I had a base memory of a gigabyte of memory, and for a 100 megahertz span, it may give me, let's say, for example, 2 seconds of seamless capture. If I reduce my span to 25 megahertz, I will increase my capture length. So for a 25 megahertz span with that same gigabyte of memory, I may be able to collect upwards to, let's say, 6 seconds. There are tables that we publish for each instrument which shows how much recording time we have versus span. It's not always linear, so you really have to take a look at the chart to determine exactly how much time you have. In general, when we get down to spans of, let's say, 1 megahertz, the amount of recording time we have is very, very long. It's in the tens of seconds in some cases.
Wow, okay. That's impressive. Our next question is, are Tektronix MDOs immune to compression effects from different frequencies?
No. There are compression effects in almost all instruments. The Tektronix MDO 4000 is what I call a entry-level to mid-level spectrum analyzer. It has a different design than a swept-tuned or a real-time signal analyzer. So in any Spec A that we work with, whether it's real-time or swept or an MDO, the control that we have to be careful of most is the reference level control. In any one of these designs, what we want to do is make sure that the peak of whatever signals in the display is as close to the reference level as possible. And if you think of a spectrum analyzer display, the reference level is the upper margin, the X line at the very top of the display. As you reduce the reference level control, or reducing the reference level, what you're doing is you're adjusting the amplifiers and the attenuators in the front end of the instrument. And what we're doing is we're trying to get maximum dynamic range possible. So usually my advice is lower the reference level until the peak on the display is as close to that reference level as possible. But at some point you're going to see an overload light come on, or an ADC saturation light, or a clipping light, or something like that. You want to back off your control a little bit from them. The MDO itself, depending on the MDO 4000A family, if it's a 3 gig model, there is no block converter. So we're looking at 3 gig acquisitions, or 3 gigahertz wide acquisitions all the time. If you get the 6 gigahertz model, it actually has 3 specific ranges. And I apologize, I don't have them memorized. But basically, if you had a 6 gig span set up on an MDO 4000, we would take 3 acquisitions and stitch the acquisitions together to give you that 6 gig span.
Okay. So I think, we're at the top of the hour. Let's just squeeze in one more question if we can. We have a question about support. What kind of support would be available for this equipment? Specifically, do you have on-site support for using the analyzer with our test unit and setup? So, with a proprietary test unit and setup.
Yes, I say yes with a caveat. Depending on where you are located, Tektronix is a worldwide organization, and we have a fleet of application engineers that specialize in pre-sales and post-sales support at the customer location.
Excellent. Okay. Well, thank you, Robin. This has just been a wealth of information, and on behalf of the audience and Microwaves and RF, I thank you so much for sharing your knowledge with us today. We're now concluding today's presentation. Thank you to Tektronix for sponsoring this event. I hope that everyone has a productive remainder of their day.
Find out more at Vicom's website.